I guess I'm pronouncing it right. Konnichiwa, minasa. Good morning, everyone. I know it's the start of the day, so let's just jump right in. Now, let's take a moment to think why we choose to use certain apps. There could be plenty of reasons. Either they are smooth, seamless, or provide a snappy experience. Or maybe most important, meeting user needs effectively. We want our apps to be responsive, perform flawlessly, and to meet our needs effectively. But what happens when our apps start dropping frames, become sluggish, or even worse, crashing in between of critical tasks? It's frustrating, isn't it? Now imagine being in the hands of the end user who is using your app and it's crashing in between. They may start feeling disappointed, lose trust in your app's reliability, or maybe worse, choose out alternatives. That's the impact of a small yet significant flaw in the app's performance. And one of the reasons could be a memory leak. Yes, you heard it right. A memory leak could be likened as a small leak which is capable enough of sinking a great ship. It may seem insignificant at first, but its consequences can be disastrous for your app and its reputation. So, in today's talk, we'll delve deeper into what a memory leak is, how it can affect your app, and most importantly, some innovative ideas around to prevent it. So, fasten your seatbelts as we navigate through the treacherous waters of memory management in app development. Let's ensure that our apps stay afloat and provide an exceptional user experience. Before moving ahead, let me introduce myself. I'm Ayushi Gupta, a Firebase GDE. So you can expect something around Firebase in this talk. A WTM ambassador. So if you have any questions around this program, I'll be around here. And currently, I'm working as a lead Android engineer at Zalando, based out of Berlin. More details about my journey you can find at my website, and feel free to connect with me on Twitter. So, after a bit about me and my current organization, let's start our journey to save our sinking ship. There is a saying, if you know it, you can deal with it. So, let's just start with having a bit of understanding around Android's memory structure. Most of the apps on Android execute on the top of Android runtime, that is ART, which actually replaced Dalvik Virtual Machine, and they both have a similarity share with Java Virtual Machine. ART uses two separate memory spaces to store running application and its data. These memory spaces are stack and heap memory, which combiningly form a major chunk of your device RAM. But that's not enough. We have to go a bit deeper. Let's just have a wider look at stack memory. Stack memory is used for the execution of a thread. It contains method-specific values that are short-lived and references to other objects which are stored in the heap. So as soon as the method ends, the particular block becomes unused and it's available for the next method. So in short, stack is more about static memory allocation. Stack is always referenced as LIFO, that is last in, first out. So it's kind of pretty fast. The size, if you look into, it's relatively small if you compare it with the heap memory. Since we are talking about size, obviously the ecosystem would put a limit on the top of it. So whenever the stack memory is hit, you're going to get stack overflow error. Now, after stack, let's just explore a bit of heap memory as well. Heap is responsible for dynamic memory allocation in your application. So unlike stack, which is used just by individual threads, heap is utilized by all the parts of your application. Whenever an object is created, it is allocated in the heap. And these objects are accessible globally. To ensure a seamless user experience, Android imposes a hard limit on the heap size as well, and that is for each running application. The heap size limit varies across the devices, and it depends directly on the RAM. So if an application exceeds this heap limit and tries to allocate more memory, it will encounter an out-of-memory error, and boom, it's a crash. But that's usually not we encounter. So what's there in background? So in virtual machines like JVM, DVM, or ART, there exists a superhero known as garbage collector. Its primarily role is to detect and reclaim unused objects, thereby freeing up memory space. Garbage collector scans the heap, identify objects that are kind of unreachable. So if we talk about, in other words, if an object in the heap does not have any reference to it, then garbage collector gonna release it from the memory. There are various algorithms that are running inside GC. This could be maybe mark and sweep, generational, or concurrent algorithms, which are helping in improving the performance. So whenever you say any object equal to null, you're telling garbage collector that, hey, please release this particular object. So now we have seen what garbage collector does for your app. After a bit about memory structure, now the question is, this was like what we have seen earlier was within the application. Now the question is, how is Android's memory managed? So right now, we're going to talk about the entire ecosystem. Android devices contain 3 different types of memories: RAM, ZRAM, and storage. Worth noticing over here is that both CPU and GPU access the same RAM. RAM is like the fastest type of memory, but it's usually limited in size. So whenever you buy high-end devices, you typically choose for large amounts of RAM because it's gonna affect your app's performance. Then there comes ZRAM, which is a partition inside RAM. So when we are talking about partition, this particular memory space can grow or shrink in size. Then comes storage, which contains all the persistent data, such as the file system, or maybe other objects, apps, libraries, and the platform-related code. And this is typically bigger than both RAM and ZRAM. Let's just start about like how physical memory or RAM is organized. When we are talking about physical memory or RAM, it is grouped into pages, and each page is typically around 4 kilobytes of size. There could be different type of pages. For example, there could be use pages, which are the pages which are actively being used by the processes. Then there could be cache pages. These are the pages that the processes are using, but some part of them is still present in the main memory. So we're gonna have like a fast retrieval of data, so we use cache pages. Then there comes free pages, which are like the pages of memory which are sitting idle on the device. So what we're going to talk about here is that I have taken a 2 GB device and I started it by doing nothing. So at the very beginning, you could see there is a flat line, right? This is when we have started by doing nothing. Now there are different applications, we start exercising them. So obviously, it's going to have an effect on the memory, right? So at the beginning, there was a flat line. This is kind of a happy state to be in because there is a lot of free memory available. And like if anything is required, the kernel can satisfy the request right away. But now the question comes, over the time, if you start utilizing more and more apps on your device, the particular free memory will start getting exhausted. It kind of goes down. Now, to avoid bad things from happening, the Linux kernel has this mechanism that particular kicks in. And we are calling this mechanism right now as kswapd. What is the job of kswapd? Kswapd is going to find more and more free memory for you. And this actually kicks in when the free memory drops below a threshold. And that threshold is called as kswapd threshold. So now if an app goes to access a cache page or memory that was on a cache page has been reclaimed, then it's going to take a little more time to reload, right? So because that reload is happening from device storage. But probably the user might not notice this. So it's like an okay state. Now I exercise more and more applications, like quite a good amount, then the number of cache pages itself gonna drop now. Now, in this particular scenario, your device gonna thrash. You might be in a situation where your device might get locked up. So on Android, we have a mechanism which is called the low memory killer that kicks in when the amount of cached memory falls below a threshold, and we are calling that threshold as LMK threshold. Now what LMK gonna do? It gonna pick up a process and just kill it. Now just imagine if it kills the process which user is using. It will not be a state we would like to be in. So this is literally a bad state to be in. If you want more details about the process selection, it could be found here. Okay, now the question comes, now what? We have seen that GC and LMK, they both work together to manage the memory in Android. GC operates within the application level, whereas LMK is operating more on the system level. There might be a situation where LMK asks GC of your app to do the cleanup and kill the entire app to release more and more system resources if there is a memory pressure. Now, what would happen if our superhero fails? It's time to bring the leak in picture, which is capable enough to sink a great ship. That is memory leak. A memory leak is just an object whose memory was not collected because there was still a reference pointing to it. And in short, it means that garbage collector is not able to take out the trash. So when the user keeps on using our app, the heap memory keeps on increasing. So at first, a short GC will come in and it will try to do the cleanup. And this short GC is on a separate thread, so you might not notice the difference. And the pause is also very less, around 2 milliseconds to 5 milliseconds. But let's say there are serious memory issues hidden under the hood. Then we need a big bro. So at that point, a large GC comes in. And when large GC comes in, it's literally a state where the device is unusable. The pause is significant. It's around 50 milliseconds to 100 milliseconds of pause. and it blocks the main thread. So app is almost unusable. If this itself doesn't fix the problem, then the heap memory of your app will constantly keep on increasing until it reaches a point of death where no more memory can be allocated to your app, leading it to the deadly out-of-memory error, and your app will crash. So let's detect these memory leaks. When it comes to memory leak, developers often turn to Memory Profiler, which is integrated with Android Studio. Obviously, you can analyze and optimize memory usage in the Android application. Through this, it allows you to monitor and you can track how the memory leaks are working. But I would say this is a proactive approach. You have to proactively monitor your app. And as we all know, we developers usually have a lot of things going on. And we tend to do profiling like later, which comes out to be never. So why not, let's have something which constantly reminds you that you have a leak to fix in. So what today we're going to talk about is LeakCanary 2, a leak detection library. And worth mentioning is that it's no more just LeakCanary. It's an upgrade that has come in, and it's way much powerful than the previous version. The internals have been rewritten to 100% Kotlin. Not only that, you can detect multiple leaks in one analysis. And you can even group them together based on per leak type. Not only that, there are APIs which are simplified now. And you can add it to the configuration, and it gives an access to the new heap analyzer, which itself is rewritten from scratch and uses 10 times less memory. What makes it different is the knowledge of the internals of the Android framework, where you could narrow down the cause of each leak, and you can actually reduce ANRs. LeakCanary will help you to find and fix these memory leaks during your developmental cycle itself. Not only that, it's gonna generate leak reports for you, and that will be exclusive for each session of your app. So once you add LeakCanary in your app, they will be doing 4 tasks for you. First is retained object detection, heap dumping, heap analysis, and leak categorization. Let's just see a bit of detail around this. LeakCanary hooks into the Android lifecycle to automatically detect when activities or fragments are getting destroyed. And ideally, they should be garbage collected. So these dead objects are received and they are passed to the object watcher. Object watcher is holding weak references. So there could be references like activity destroyed, fragment destroyed, or view model cleared, right? And not only that, if you want, you can watch any object of your choice. So what happens now? Once we have the weak references, we wait for the 5 seconds, and then we execute GC on the top of it and see whether the object is getting cleared. If not, then it is considered to be potentially leaking. LeakCanary keeps the count on the number of retained objects. It waits till the count of retained object is less than a threshold. This threshold value is 5 when the app is in foreground, and it automatically sets to 1 when the app goes in background. And as soon as the count crosses the threshold, a heap dump is triggered. I guess this particular toast is known to most of you. When the count of the retained objects crosses a threshold, LeakCanary dumps the entire Java heap into a .hprof file. And this particular process takes a bit of short amount of time, and that's where you see this particular piece of toast. What happens in heap analysis? In this particular step, leak canary gonna parse the hprof file using Shark, which itself is a standalone library, and it is called as Smart Heap Analysis Reports for Kotlin. It locates all the retained objects in the hprof file and go to each particular path references of that object and see what actually led to that particular leak. And not only that, it creates a signature of each leak trace and groups them together so that it may be easy for you. Maybe it's because of same bug which is leading it to the same leak. So if we have a closer look at the leak signature, which is like the hash of the concatenation of the references, each reference is suspected to cause the leak. And even they have, like you can see there are underlines which tell us that yes, that could be a reason too. So now we have every information that could be extracted from the hprof file. But we use a lot of different libraries in our code, and there might be a situation that the leak is coming from your library. So leak canary separates the leak it finds in your app into two categories. First are the application leaks, and then comes library leaks. You can say library leaks are the leaks which are coming from third-party code, and maybe fixing it may be out of your control. So leak canary separates it out. So now we have seen all the capabilities of leak canary. Do we have something like now it's the time we can wire it into our developmental cycle? So why not, let's just add it into our code base. If you notice now, the dependencies have been simplified. Now we have debug implementation, release implementation. So when we are talking about debug implementation, it will not have any referencing into the release builds. Worth mentioning over here is that release implementations are experimental right now, but you can use it and play along and see what data is coming from your apps. Just to mention is that there is no more referencing to any other Android libraries now. It's all been done automatic now. This is something which really interests me because any feature development is not completed until we have testing implemented. So leak canary 2 now has an artifact that can actually help you to detect leaks in your testing cycle itself. If you add this dependency, it will take care of it. So let's just try to integrate leak canary with our UI testing. It's pretty simple. You just have to add leak assertions.assertNoLeak at any point of your UI testing cycle, and it will detect whether that particular piece of code is leading to a leak. And if there is a leak, then the entire process which we have seen will be initiated, and your test will fail by giving you no leak assertion fail error. So testing is sorted now. But I would say, let's say you have a file which have many number of tests. Then in that scenario, maybe writing leak assertions.assertNoLeak at the end of each test might be tough. So now we have rules as well which you could use. So it will automatically execute leak assertions.assertNoLeak at the end of each test case. So that's okay. Now let's say if you're working on a fix of a leak and you want to fix your CI/CD, so you can use @skip leak detection annotation. It will disable the leak assertions.assertNoLeak, and your CI/CD could be a green. So we have added the leak testing in our test classes. Now we have all our tools ready. It's time for the quest of cleanup. Before we take a step ahead, let's just evaluate a developer strategy. So usually a development starts with a product requirement. You get it, clarify it, and start working, right? Once the development is done, you test the functionality on your own or maybe with your QA team, and get your PRs merged and done. Now, in this journey, as a developer, very rarely you're going to go and check leak canary logs, which were actually captured during your feature developmental cycle. So why not let's just add leak canary 2 into your developmental cycle itself. So let's just see a bit of code here. Let's just try to wire it in the developmental cycle. As I mentioned, leak canary 2 has simplified access to heap analysis process. So now we're going to use it and we're going to implement a listener to the entire heap analysis process. So if you see over here, we have added an event listener for the heap analysis success data class. And we're going to pass that entire information to the leak canary upload service. But make sure that you update your configs as well. So this particular piece of code can help you out. Just you have to copy your event listeners plus the listener which you implemented. Now the question comes, what is leak canary upload service? So in this service, we're going to do a proper extraction of the heap analysis success data class. We'll extract out the both application leak information and the library leak information. Once you have the data, you can transform it the way you like, but make sure that you preserve the data format so that once you try to reread it again, you can actually read it, right? So maybe something about custom stack trace builder can help you over here. Now we have everything, right? But the question comes where we should visualize our leak traces. On a better scale, maybe something like real time, and where you can actually see how many developers faced it. And most important, I don't want to add any more dependency in my code base. So why not wire it through Firebase Crashlytics? Firebase Crashlytics is currently part of most of the Android apps. It's pretty lightweight, nearly a real-time crash reporter. Not only that, you can easily track how many users, what's the device capabilities, and things like that using Firebase. You can easily prioritize by seeing how many developers are actually being affected by that particular crash. And there is an additional payload capabilities. You can add as much, like not as much, but some information in that particular crash. Okay, now if we talk about the code, it looks something like this. So here, worth mentioning is that we're going to wire the leak canary information as non-fatal crashes. We will not going to affect any of the production numbers. So we have the information, we play with it and pass it to the Crashlytics. Let's just see how it looks on the Crashlytics. So the data is nicely preserved. You can separate out application and you can play with it now. So if you recall, we had a conversation regarding leak assertions.assertNoLeak, which is actually delegating the call to the global detect assert implementation. So you can utilize this function and add it the same capability that we did for the application in your testing cycle itself. This functionality will actually help you to detect vulnerabilities in testing. So when you're running your test, your CI/CD will automatically catch all the vulnerability tracking information on Crashlytics. So we have safeguarded our testing cycle itself. And here comes one more thing. When we are talking about Firebase, we have to think about Firebase integrations that comes in with Firebase. Let's just see what are the few additional capabilities that we can add to our journey. First, I would like to talk about Jira integration. With Firebase Crashlytics, you can easily integrate Jira and have your tickets ready for your leaks. Then comes Slack integration. So you can easily wire Firebase Crashlytics with your Slack. Just a tip over here, you need to replace on new fatal issue payload with now new non-fatal issue payload because we have logged our crashes as non-fatal crashes. If you want more details on this, it's there on the official documentation of Firebase Crashlytics. Memory leaks gonna cost you a lot in terms of your app performance and in turn user retention too. So here are some do's and don'ts that you can incorporate in your coding style to avoid leaks. I'll not go into detail of it, but yeah, this could be something which could help you out. These small steps while building the app can actually help you to deliver high performance Android apps. Detecting, visualizing, and fixing memory leaks will not only make your app's user experience better, but it will slowly turn you into a better developer as well. Leak detection can tell you when there is a code smell or bad coding patterns before they get baked so much into your app that they actually haunt you to fix. Leak detection can teach developers to write more robust apps where we are taking care of low-end devices as well and making sure that they get the same experience as high-end device users. No doubt, development is an ever-going journey, but these small things can help you to save your ship from sinking and can set the course of selling it high. Just before we conclude the session today, some food for the thought. So let's give this session a wrap for today. Thank you everyone for being patient listeners. And let me do a justice to my Japan trip. Arigato.